Okay, so what I like to do is now connect some of the pieces that we've been learning so far about injective, surjective, bijective, and left inverse, right inverse, and inverses. So there was an example that we've looked at now in both section 4.3 and 4.4. So this function that maps the reals into the non-negatives given by x squared, we showed that this has no left inverse, but it indeed has a right inverse. It actually had multiple right inverses. Now, we also just showed that this same function with the same domain and codomain, it is not injective, but it is surjective. So if we go over here about some facts, the function f has a right inverse if and only if f is what? So looking at this, we should be able to see from this example, no left inverse, does have a right inverse, not injective, but it is surjective. So this is going to be f is surjective. So here the function f has a left inverse if and only if f is injective. Right, exactly. Injective. And the function f has an inverse if and only if f is what? So on the count of three, everyone say it. 1, 2, 3. Bijective! Yay! Bijective. Excellent. All right, so we have these statements. So what this allows us to do is if we want to show a function is surjective, we could do the regular proof of surjective, or we could instead show that it has a right inverse. Same thing is true about injective, right? We could show that it has a left inverse, that it is injective, or vice versa, right? So if we want to show that it has a left inverse, we could show that it is injective. These are equivalent statements. Remember, the if and only if allows us to know that both of these two are equivalent. So we have these statements and they're really nice, but we'd like to try to build some intuition of why is there a relationship between these two various ideas about left and right inverses versus injective and surjective. So if we take a look at just an example of this, let's say we have A and B. Let's say we have this function f maps A to B. And then if we're going to talk about this inverse, we're going to work with, say, G, let's go B to A. That way we can talk about both left and right hand inverse in a meaningful way. So remember, so if we said it has a right inverse, what that's saying is that means that the inverse is going to appear on the right of a composition. So that'll be f composed with G of x is equal to x. Or in other words, we're saying that f of G of x is equal to x. So this is what it means to be a right inverse as a reminder. So if we think about what's taking place here, why is there a relationship between surjective and a right inverse? So if we look at this element x, we're plugging this into our function. This x value has to be in the domain of G, right? So we have to allow ourselves to put this from our x is an element of B, and then what pops out then is again an element from B. So we're visualizing this right inverse. That means that I'm going to take something over here, let's say this x, I'm going to go this way first with G, and then I'm going to go back with F. This is my composition. I take x, I look to see what is G of x, and then I go back with F. So if we think about how is this a well-defined function, right? So if we think about what are some things that we must have for a function, well, one of the things is that every element in the domain must have something that it gets mapped to in the codomain. So if we take an element here that we're starting with, where we're starting with is that the domain of G. So we're trying to figure out how do I have the restriction that every element in this set B has something that it's going to be mapped to. Well, because all of this is still based off the function f, we define f and then we can define g. Well, f, if it is surjective, then that means that every single element in the codomain must have something that mapped to it. So because there's no leftovers in the codomain with a surjective function, that allows this G to be a function with having every element in the domain of G have something that is mapped to because of F mapping things in the domain to the codomain. Now, the tricky part here is that what about the injective part? Because you're like, well, wait a minute, yes, that makes sense, but well, why is it that the right inverse works for surjective, but it doesn't work for left inverse? So if we look at something like this example, and we say this would be another element, and this is not injective, right? There's two elements in my domain that get mapped to the same element in my codomain. So the thought is, well, yes, okay, I have this element here that when I apply G to it, I get mapped over this direction, and then F is going to map it back here. But I thought we said that a domain, or that a function has to have every element in its domain get mapped to exactly one element in the codomain. So this is an issue, right? Because now you're saying if this is well defined, right, as a function where G, this is not okay. I cannot have one element get mapped to two different outputs. This is where we saw in the example that we did see this case, there's multiple choices of a right inverse. So we can define our right inverse to be one of these in one case. So it allows us to kind of like slim down the choices that yes, even though there are two choices, if we have no other restrictions, we then force that added restriction and still show that it works. Because the important part is that we get this composition returns to the original. So if I instead don't choose to follow this path, I restrict it to only saying I'm gonna choose the top one here. Then when I go back, I still get back to this original input that I had. So this is the same way when we looked at the example, the right inverses, we had the example of the square root of x, and we had negative square root of x. We just created this rule that says I don't care about the choices of the negative ones, for instance, when I looked at just the square root of x1, or vice versa, I only cared about the negative ones when I looked at the negative square root of x, and I ignored the positives. Okay, so that's the intuition behind the right inverse with surjective, then the left inverse being injective. Again, we have a similar idea, but now for a left inverse here, we now have g of f of x is equal to x. And now we're taking instead our function, instead of starting with an element in the domain of G, we're starting with an element in the domain of F. So we instead can look at this case here, where I'm going to take this element over here, X, I'm going to feed it through the function F first, I end up in B, and then this other function G is going to take that back and hopefully line it up with the same element to have ourselves a left inverse. So again, using a similar thought process with the left inverse is equivalent to something being injective. We see again that if we want this to be okay, an issue is that if I had two elements that then got mapped to the same thing over here, then what's happening is that every element in my domain, that's fine, it gets mapped to something in the codomain, but when I go back to this process, G has this question now of, yes, I have this input for G, but am I going back to X or am I going back to Y? I shouldn't have a choice with a function, right? So for G to be a well-defined function, it only should have one choice. And we can't restrict it anymore in this case like we could in the other instance, because we still need to have every element in the domain of F be mapped to something in my codomain. So this is where if it is injective, that if we allow ourselves to have everything get mapped to only one other choice here, well then yes, I should be able to go forwards and then I could go backwards. But similarly, if we're trying to figure out, well, why does that fail with something not being surjective? Well, we notice if, say, this is our function, I can map F takes the elements of A, everything over here gets mapped to something into B. But G needs to be a well-defined function, but if it's not surjective, then there's nothing that got mapped to this element down here from F. So when G's trying to figure out where does this element go, it doesn't go anywhere. So this is no longer a well-defined function for G. So that's where this left inverse fails when it is when it is not, or when it is not surjective. Wait, you get the gist, I think. So nonetheless, so now if we look at this statement here about it being bijective, what we're basically saying is that f of g of x is equal to x and g of f of x is equal to x. And as we saw on the example that we looked at of the two functions being bijective, we basically have every element here is going to have a unique buddy over here that it's going to get mapped back and forth to. And so everything over here only has one and only one. So this is basically this perfect matching, and that makes sense that in either case, you either go this way and that way, or you go this way and then that way, and so you get perfect back and forth movement. And so this is where a well-defined inverse function is going to be when you have a bijective function.